But anyway, so I've been writing C for, I thought about it today, I've been writing C for over 20 years now, which is really kind of scary, I guess. But these days I'm a system engineer at something of a startup, which basically means that I write a lot of software and turn a lot of screwdrivers and try to make customers stop yelling at me. So with that in mind, I've got a presentation here for getting started in firmware. And I'm going to take a slight different take on it. I'm going to talk about concepts in the big picture and how things are executed. And there's going to be no code in there, except for one little thing, but no code. So it should hopefully be something that you can get into pretty easy. I'm kind of coming at this from a standpoint that maybe you've written some programs before, maybe you've got an idea of playing with firmware stuff, or you know, you've got a little bit of an idea of how a computer works, but maybe not the big picture. Hopefully we can demystify some of the stuff about how do you actually make that little processor do something useful. So, that said, first question is just what is firmware? So firmware is typically software that gets burned to a microcontroller, flashed in there, and a lot of times it'll never get updated. You're going to write the code, you're going to flash it, you're going to spew it out into the world, and you'll never see it again. So with that, you have to think about writing your code in such a way that it'll last its lifetime. I mean, sometimes the lifetime is 3 months and then it gets put on a shelf. And sometimes, you know, it's going to end up being out in the world for years and years, and people are going to exploit it in ways that you never expected. But, you know, that is life for firmware. So we talked a little bit about the goals here that we wanted to cover in this class. So I'm going to go over the basics of program execution, kind of compare and contrast, like a desktop PC and executing on firmware on a microprocessor. We're going to talk about how data is handled by your CPU, how data gets in and out. That's always a very important part is, okay, I can make it execute on here, but if I can't talk to the outside world, it's kind of useless. Some of the basics of programming for dedicated hardware, and we'll talk about development environments and some common pitfalls. And please do think up some snide remarks. There's going to be a section later for that. All right. So first off, let's look at running an app on your typical PC. Okay, so you double click on the desktop and your app launches. That seemed pretty easy, right? There's not much to it. But in the background, there's a process scheduler that's busily running your app and then sharing time with other apps. And it's doing that all in the background, so you don't have to worry about it. But below that, you have a hardware abstraction layer that's abstracting the interface to the hardware. So there's a common interface, so it doesn't have to worry about, I've got an Intel Ethernet card, I've got an AMD Ethernet card. It just handles the abstraction. But below that, you have device drivers that actually speak to the actual hardware. But below that, you have the operating system that's handling all the device drivers and the memory access. And then below that, you have the BIOS, which is handing off all that stuff to the operating system. And finally, below that, you've got the bare metal CPU that it's actually executing on. And of course, below all that is turtles all the way down. Now, let's compare that to the app you're going to be running in your firmware. So, your app fires up, but what's underneath your app? Whole lot of nothing. So when you're writing an app for firmware, you have to handle a whole bunch of things. I mean, you still got the turtles, so you got that going for you at least. So looking at this, what's missing? So your app is responsible for booting the CPU, setting up all your hardware, managing the execution of your program, managing all the memory, and managing all the I/O. Sounds like a lot of work. I mean, going from writing a desktop app where most of that stuff is kind of magicked away for you and you don't have to worry about it much, going to writing something like this where you actually have to handle it. So, you don't have to implement the whole thing, right? So you don't have to generate a whole operating system because only your app's running. You don't have to let his app run, you don't have to let this guy's app run, you just have to run your app. Which means you can take a lot of shortcuts, right? So, here's what you need to do to get your firmware going. Study the chip docs, figure out how to boot the CPU, right? Study the chip docs, figure out how to set up your I/O peripherals. Determine the memory map of your system and write a linker script. Write a CRT0, it's a C runtime 0, which is basically the little program that the chip boots to, sets up memory, copies memory, static variables into RAM, and then hands control off to your application. Well, that's still too much work, right? But the good news is that from almost all the chips that you're going to want to work with, someone's written a tool chain or a board support package where you can just download that and install it, and it makes writing your app a lot easier. You still have to study the chip docs to kind of figure out how to set things up, but the nice thing about the BSP is it's going to handhold you a little bit to allow you to basically start in your main application and not worry about some of that stuff. So the bare metal and the turtles is going to be somewhat handled for you. So that's the name of the game for all this, is abstraction, 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 right? All right, so let's talk about data a little bit. So first thing you worry about on processors is endianness of the data. So when you're looking at bytes, right? So a byte is 8 bits. I'm sure you're familiar with that. But the question becomes is how is that data actually represented in memory and on the wire? Do I hand you the big byte first, the one that has the highest numbers, or do I hand you the little byte first? So there's a couple of different ways of going at this. There's actually 2 ways of going at this. It's either hand you the big end first or the little end first. Motorola went with the big end, so sometimes people call that the Motorola byte order. Intel went with the little end, or so sometimes people call that the Intel byte order. Network byte order is big endian. So stuff going over the internet is standardized on big endian. So that's pretty easy to deal with. In any case, the bits in a byte are always in the same order. So these guys and these guys are always in the same order. So the most significant bit is always this bit over here on the left, right? But when you flip the bytes get flipped. So the most significant byte gets shuffled over here to the least significant byte when you swap between big endian and little endian. For the most part, you don't need to worry about this. Like when you're writing code, if you're going to keep on one processor, you don't have to worry about what endian is. This gets kind of wacky when you start doing data interchange. So I want to send you a byte stream. Well, I need to know, do I need to flip my bytes around before I send it to you? Or can I just send it to you as is? So if you're using a bunch of chips that are all big endian, then you don't have to think about it too much. But if you've got a chip that's talking little endian, you might have to flip the bytes as they come in so that things make sense. So it's something to think about. So if you get into it and you start transferring data, and you're getting data, but it's like all backwards of what you expect, you might have to do some byte swapping. All right. So the next thing, let's talk about parallel versus serial. So the nice thing about parallel is, let's say you have 8 pins on your processor, you can send a whole byte over to the other side at once. You set up all the pins, send it over, hey, here's a whole byte. Just lobbing bytes at you, right? It's nice and fast, but the problem is I had to use 8 pins to do that. And you've seen some processors, I mean, some of them only have 8 pins. So how the hell do you make that go? But what you do instead is you can send them serial. So basically I use 1 pin, and then I say, okay, here's the first bit, here's the second bit, and you have to have timing set up so that you can figure out where's the start of the bit and where's the end of the bit. So it's slower to do, but it saves you a lot of wires. It also means that you need to have some buffer in your processor to handle pulling in these bits and reassembling it into bytes. The good news is that there's hardware that handles this for you, but it's good to know on the low end what you got going on there. So next thing you know is memory maps. We talked about this a little bit. So you're going to want to look at, based on your whole system, and this may not even be one processor. This may be your system at large if you actually have a system that has a memory bus sort of thing. But what you would have here is you would have, like at the bottom of your memory map, so imagine you've got a big chunk of memory there, so it's a bunch of bins. Like imagine like a letter, like a post office that has a bunch of bins for mail to sort into. Different bins have different purposes. So some of them might be special function registers. Some of them might be peripherals. We'll talk about that in a minute. Some of it might be RAM. So the nice thing about RAM here is you can read and write to it, right? Some of it might be ROM. This is where the code you wrote gets flashed out to And ROM, you usually can't update while the program is running, which is a good thing. You don't want to accidentally overwrite your actual program code. Because remember, you know, this thing goes out in the world, it may never update again. So you want it to be able that you can yank the power and plug it back in and it goes back to a known good condition, right? And then you have wacky things out here like interrupt vectors. So in general, when you see the word vector, what they're really saying is this a pointer? So in your flash space, so your code compiles down, you have a start of a function, right? So here's a start of a function. A vector basically says, hey, when you want to go to this vector, this is actually a pointer back to go to this function. So the processor would hit the vector and say, oh, I need to run this vector. Okay, I run this function. So it runs that function. So it's pretty simple once you kind of figure it out a little bit. So in addition, there's something called memory mapped I/O, which you've got this RAM space, but sometimes RAM isn't RAM. Instead, there's I/O ports that are assigned to different peripherals. So you might have a certain memory address that if you write bytes there, it actually squirts out of a serial port, right? Or into some sort of special hardware. Or there might be another address that if you read that, you get data that's coming in from some peripheral out there. So it makes your peripherals look like memory. So it's kind of weird to get your head around a little bit, but it makes it really easy to get data in and out of a processor, because from a processor standpoint, it's just more data. It's just an offset that it reads or writes to, right? So we talked a little bit about registers. So this is something you might see in a chip dock, right? They'll specify this register, which is the MCU control register, and they give it a funny name there. A lot of times what you'll see when they give it this abbreviation, the tool chain will set up a define for this so that you don't need to know the offset. So you see here it doesn't actually say what offset in memory it is. It's just counting on the tool chain to set that for you. So let's say that offset is 80 hex or something, right? So you don't need to worry about 80 hex in memory is where this register is. It's just that name, right? Abstractions are good, trust me. So in these registers, there will be various bits, and the bits will have different jobs to do. They'll indicate whether these are read or write. Some registers are set up so that they're write only. You can only set a configuration variable, you can only write to them. Other registers are set as read only. You can only get data from them. If you try to write to them, undefined behavior happens, right? It could be innocuous, it could be something bad. Just don't do it, right? It'll also tell you what the initial value is for these things. So we can see here for like this SM, the sleep mode index bits. So you got 1, 2, 3 bits here, which for whatever reason they decided to skip that bit. I mean, I don't know, let's skip that bit, right? If you set the bits in these orders, it allows you to set these different kinds of sleep modes. So this is where I talk about reading the chip docs to figure out how to set up your hardware. If you wanted to say, I really need to have that ADC in noise reduction mode, then you would want to look to see, okay, well I need to write a 1 bit to this spot in this register in order to get that feature enabled. So this is how you configure your processor to enable and disable various features, various parts of the processor. So the other big thing to worry about is what's called the stack and the heap. So if you imagine this is a big contiguous block of memory. So here's offset 0, here's offset 1000. At the bottom of the memory, you're going to have your static memory. So let's say you wrote some code and you had a global define that said that Bob is equal to 10. Well, when it gets loaded out to memory, out to your flash, it's going to point to a certain location. Let's say location 0 is that Bob address. When it starts up, it's going to take that 10, preload it into this piece of memory, and forever on, whenever it wants to figure out what Bob is over here. Any variables that you create when you go into a function, like you create a new variable for pip, for instance, in some function, it's going to go onto the heap. When you call another function, the calling parameters that you send to another function go onto the stack. Now, the way this works is as you use more heap memory, your heap pointer, so there's 2 pointers here that are pointing to the end of heap and end of stack. As you use more heap, the heap pointer is going to go up, And the stack pointer is going to grow down. So it's going to start out at 1,000, it's going to go to 999, 998, and work its way down. So the important thing is don't cross the pointers. Just pretend, you know, your Ghostbusters there, you don't cross the streams because that's bad. If the stack pointer crosses the heap pointer, then you've overwritten memory, and now the processor is going to go off in la-la land. So you have to be careful about that. You can also think about these in terms of like caving, right? So you've got stalactites coming down and stalagmites coming up. Try not to make any columns. You know what I'm saying? Or maybe you don't. I don't know. So, interrupts. You may have heard of interrupts, maybe not. Interrupts are basically hardware routines that you can sometimes configure. Some of them are baked into the firmware, where what you want to say is, here's a program execution going forward, but when something happens, I want you to pause the main program execution and jump to another function and do something else for a moment. For the most part, you want your interrupts to be fast. You want to get this done fast and get back to the main program. You don't want to dilly-dally over here, because when you're in an interrupt, depending on the processor, you may not be able to get another interrupt. So you want to do that quickly. Here's an example of like an interrupt vector table here. So some of these things, you've probably seen some of these things in the past, like general protection fault. Who's ever seen a general protection fault on like an old PC, right? These sort of things are ones that you can't really configure. Like there's probably a divide by zero error in here, those sort of things. If something bad happens on the system, it reads a bad piece of memory or something, it's going to, like a page fault, it's going to jump to this interrupt vector, and if you have a handler installed here, then it's going to call your handler and do something about it, right? So this is how you can save your bacon if something bad's happening, if you actually write an interrupt vector. A lot of times, maybe you don't care about these things, and you write a default one, and the default one is usually halt. So it just puts the CPU in a spin. So that can be useful sometimes if you've got something that's really important and you're detecting errors. You can just say, okay, stop what you're doing. You're not doing a good job of this. Just sit in the corner for a while, right? But it's good to know with interrupts, this is an easy way for you to pause your program execution and go do something else for a little while. All right, so booting your CPU. There's going to be somewhere in memory, and this is hard-baked in the CPU silicon, that it's going to go look at the reset vector. It's usually address 0, but it can vary based on your processor. And the reset vector, all it is an offset to tell the CPU where to jump next to start program execution. If you don't have a bootloader, for instance, it's going to jump over the interrupt tables and go right to your main function here, your very first piece of code, the CRT0, and start executing your code. If you've got a bootloader, maybe it'll jump into bootloader. Bootloader will decide, should I bootload? If not, then I'm going to go ahead and jump into the user code. So that's how the memory map would look if you're running a bootloader, for instance. The nice thing, if you're not familiar with bootloaders, the nice thing with a bootloader is if you want to update this, you can have a special piece of code that only runs at power on to try to update itself via some method. Over a serial port, over a network, whatever, right? But the important thing to know is that the CPU doesn't care what this is pointing to. If you point him into the middle of code out here where you point him to like the Bob address, let's say, he's going to jump out to Bob and load it into the processor and try to execute it as an instruction. And if it's not an instruction, maybe it's something fun and it'll go do something else and your processor just goes crazy. Most of the time, though, the processor will just lock itself into a loop and you'll be like, why isn't the light blinking? The light should be blinking right now, right? All right, so let's hop into peripherals. So your basic peripheral here is your general purpose input-output. So this is just a pin on a processor, right? All CPUs are going to have some sort of GPIO. This is how you get data in and out of your processor, barring special peripherals. The good thing is that you can do what's called bit banging to emulate special peripherals. So let's say you ran out of serial ports, but you really need one more serial port. Well, it's possible to emulate one of those in software, but the problem becomes is that it takes a lot of CPU time to do that, right? So you're spending a lot of time emulating some sort of protocol that some piece of hardware can dedicate itself to doing. Reading and writing to a GPIO is really simple. Like, remember that memory mapped I/O thing I said? You can just write bits out to it. Write a 1 to it, the pin goes high. Write a 0 to it, the pin goes low. Or read it. If the pin's high, you get a 1 back. If it's low, you get a 0 back. Super simple. You also have to worry about pull up and pull down resistors. So what are those? Well, logic inputs can only read either 0 volts, that way, or VCC, which is your whatever your voltage rail is, 3.3 volts, 5 volts. If you leave it floating, if you didn't have this and you open the switch, there's nothing to pull this guy up or push it down, and it's going to be floating. And what you're going to see is maybe this thing will think it's a 0, but a lot of times it'll sit there and bounce, and maybe if you touch the board just right, it thinks it's 1, maybe it's a 0. And I should probably take probably out of this because you're going to see something wacky going on.
Could you explain a little bit more what you mean by push and pull?
Sure. So here's your 5 volts here, and here's your 0 volts here. Okay? So binary is either 0 or 1, right? Processors speak 0 and 1. They don't understand the colors of gray in between. They don't understand like almost a 5 volts, or they don't understand like 2 volts. They only understand it's got to be up here, or it's got to be down here. So if you're not actively pulling it, so looking at this circuit here, we've got a resistor here. This is kind of a high value resistor, let's say. When this switch is closed, this resistor is conducting, but from this guy's standpoint, he's seeing pretty much 0 volts there, which means that he's going to get a logic 0 coming out this end. Now if I open the switch, there's nothing to pull this voltage down here, so he's going to see the 5 volts or whatever that's up here, so that's going to pull him almost up to 5 volts to where he's triggering, hey, I've got a logic value of 1 coming in. So it's literally like a tug of war sort of thing. You always want to tug one direction or the other. You never want to let it float in the middle. Does that help you any?
Yeah. So in this situation, you're talking about actually physically breaking the circuit, kind of, right?
Right.
Because if you have the circuit open, then the voltage is weird and it's not going to read right, because you actually have to pull ground down and have a 0 voltage on there for it to register, right?
Correct. All right, so let's look at a couple of peripherals that you might see other than GPIO. So these are all serial kind of protocols. So there's stuff out there called SPI ports. So a serial peripheral interface. It's wired up in such a way that you have one master and multiple slaves. The way you select which slave you're talking to is you have a slave select. So like MOSI stands for master out, slave in, master in, slave out. So this is getting data from the master. This is pushing data back to the master. And the way it would work is I would send data in here, and at the same time I'd start clocking, saying, okay, read the data now. Okay, I changed the data. Okay, read the data now. So there's a signal going on that says when it's okay to read the data. And the slave select chooses which one of these 3 gets the bus right now. Serial. I'm sure you guys have used RS-232 ports. I mean, you know, back in the day, dialing up with your modem, you used a serial port connection. They're stupid simple. They're great. They're asynchronous serial. The downside is except for like 422 and 485, they're point to point. So I can only talk to one device ever. You can't put a third device on the network without having some sort of weird arbitration there. And then you have things like I2C, which is like this guy, but they're only using 2 wires. These guys have addresses. So you send out a specially formatted serial string that says, I want to talk to device 12, and here's the command I'm sending you. And then device 12 will send back and say, I'm device 12, here's the result. It's nice because it has less wires, but it also means that you have to have more code to handle these device addresses and such. Even more peripherals. So talking about getting voltage levels in and out, you have things that are ADCs and DACs. Analog to digital and digital to analog. So these are used a lot like to capture my voice, for instance. You'd have an analog to digital converter. So it's getting some sort of analog value in. It's creating an approximation of that and turning it into a series of bits coming out. So let's say 5 volts is 1024, 0 bits is 0. Well, 2.5 volts may be 512. right? So you can take these levels and you can approximate a digital input. It'll still be a little choppy because, you know, the more bits you have, the more fine grain you can go, but you also have noise introduced in there, et cetera, et cetera. Same thing with a DAC. You can send a digital value out and get an analog signal out here. So it allows you to drive speakers, and, you know, this is how you listen to your music. You've probably heard about DACs, you know, quality DACs, piss poor DACs, you know, that sort of thing. The other thing is these can have different interfaces. They could be parallel or serial based on how quickly you want to get data in and out of them. All right, so let's move on to some programming basics. So for firmware, your typical program structure sets up the hardware, and then you jump into a never-ending loop waiting for something interesting to happen, and then you do something amazing, and then you go back to waiting for something interesting to happen. So this is super simple, right? So for an example here, you set up your GPIOs to detect a button press. When the user presses the button, you send them insults on the serial port. And then we go back to waiting for them to press another button. Maybe they never press another button because they got a bad insult, who knows. But you get the idea. This is the basis of pretty much all programs you're going to run in firmware. You're almost always going to end up with some big while loop that it's just a while loop and it's going to run forever. So let's talk a little bit about, we talked about interrupts a while back, about pausing interrupt or pausing program execution. So you probably heard about polling, you know, pulled I/O kind of stuff. So polling means that I'm sitting in this main loop, and every so often I have to check out and say, is Nemus asleep? Is Nemus asleep? Is Nemus asleep? Over and over and over again. Whereas if I can set up an interrupt over here, I can go off and work on something else over here and wait for the hardware to say, hey, Nemus is finally asleep, guys, and do something interesting over here. The downside about this is that you're waiting till, like if this piece over here isn't going to do anything until Nemus falls asleep, and he's off doing something else, then it gets a little bit more interesting if you need to stall program from running until he falls asleep. The other piece of it is this timing piece here. I see absolute timing like wall clock timing, right? If I want something to happen once every second, if I'm sitting in a poll loop, I can't guarantee execution of that poll loop. Maybe I got busy for a minute checking if Nemus was asleep, and I come around here and it's more than a second, less than a second. If you can set up an interrupt to fire once every second, then that gives you really good wall clock time so that you can fire once every second. I'm guaranteed to check if Nemus is asleep. So direct memory access, or DMA, this is kind of like magic in a way. What you can do is, by using DMAs, that you can take the CPU out of the equation. If you're doing programmed I/O where you're passing data out of a serial port, for instance, you're taking the data, the CPU is taking the data here, picking it up, sticking it over here. So he's doing, you know, the fireman kind of, you know, carry the bucket across. Well, what if we could just tell the serial port, don't bother the CPU, he's busy checking if Nemus is asleep. Instead, I want you to go right out to memory where it's coming in somewhere, reach out to the hard disk, grab the data in the background without waking me up, and send it right out to serial port. So DMA is really awesome like that. But not all devices support DMA. Some do, some don't. It kind of depends. So that's something you might run into. All right, moving on. So that was a very quick overview of hardware, very quick. So you know, it may have been a little too much, but it kind of gives you some ideas, get some terms going in your head, etc. So let's talk about programming. So first off, what language do you want to program in here? Well, you may want to try like a high-level language like Python or Ruby, where you can do things like import sandwich, add slice of cheese, eat sandwich. Hey, that's great, right? 3 lines of code, I got my sandwich. But the problem is, it's probably not what you want, because by the time you bring in the interpreter and all that stuff into your little bitty microprocessor, you may have eaten up all the RAM and you have nothing left. However, sometimes if you select your chip carefully and you've got a lot of RAM, there are micro versions of Python and Node and such, so you can write in those languages if you really want to. That could be really useful if you're trying to share something out with a bunch of people and you expect them to create code on the fly. but you know, it's going to take a lot of space to get you to your sandwich. So assembly, well, I wouldn't wish that on any of you guys, really. I mean, assembly's fun and all, but only if you're into painful kind of stuff, or if you just need that last bit of speed, like you want sandwiches flying out of this thing, and you don't care about that cheese so much, but you need those damn sandwiches, then maybe you need assembly, right? So a good middle ground here is to go to C. Don't like C? Seriously, tough cookies. I mean, C is great because it's one layer above assembly where you can still talk really low level but still be a human. You know what I'm saying? So I would highly recommend that if you're going to program for microcontrollers, that you learn some C. It's really not that bad. Trust me, guys. I mean, I know I say I've been doing it like 20 years, and I'm mostly sane. I mean, I look sane, right? So, IDEs and Toolchains. Next piece of it, you know, you got your C. Are you going to write everything in Notepad? Well, I mean, I guess you could, or maybe you're a Vi kind of person, or Emacs, or yeah. We're not going to go there, man. We're not going to go there. So, you might be tempted to go to the Arduino IDE. Hey, it's a good start. Arduino's nice. I mean, you pull it up, you bring in your board support layer, you bring a couple of defines in, you write, you know, print hello world, and you flash it out to your chip. Hey, it's working. That's awesome. And there's no shame in using Arduino IDE. That sounds really rough, but the problem becomes with the Arduino IDE is that it really wants you to write everything in one file. So if you're doing something basic, like you're trying to check if Nemus here is asleep and then kick him every 5 minutes, right? You know, Arduino probably worked for you. But if you've got something where it bloats into like a 10,000 line program, it probably makes sense to break that up into separate files. And the Arduino IDE really doesn't like to let you do that. The other problem is a lot of the drivers that you can download for Arduino are things that the community have put together. And you might find that, like, you download this driver and you've got it working great. If in 6 months from now you go to program it again, so you download all the same stuff, well, Billy Bob here that wrote the driver said one night, you know what? It'd be great if I changed everything about the interface. And he uploads it, and Arduino pulls down that library, and now your code doesn't work anymore, and you've got 5 hours to figure out what's the difference between Billy Bob 1.0 and Billy Bob 1.2, right? So it's a good start, though. It's a good place to start. Chip makers, a lot of times they have IDEs, either free or for paid. They're a good place to go. You kind of get locked into their walled garden. That's really what they want. A lot of times what they'll do is it's all free until you get a few kilobytes worth of compiled code, and then they want that license from you to compile more than 5K, 10K, whatever the limit is. And that license can be like $100, or it can be like, I have some software that I use at work that we spend $1,500 a year on just so we can compile some code. A lot of times you can find GCC out there for it. So you can find GCC and a new lib and you know, all that stuff to actually compile and flash out to your code. It's a really good option. This is my recommended option, is try to find GCC for it. There's a lot of developers out there. There's going to be a lot of help, but it may still be bleeding edge in some places, and you might run into some weirdness. But hey, you know, if you're into that sort of thing, you might be able to contribute right back to it and make it better. So, I mean, some of this applies to Arduino IDE as well. Maybe you can help Billy Bob out to not screw up his interface next time. You know, that sort of thing. All right, the other piece that you can have here is there are real-time operating systems. So these are tiny little kernels that manage memory and task scheduling and task-to-task communication. And it's really nice. There's a bunch of them out there, like Chibios is open source. MQX is one that I use that's not open source. I guarantee everyone in this room owns a device that runs VxWorks. A lot of routers like to run that. Linux can be a real-time operating system in some flavors. And you know, you go to Wikipedia, there's a list this long of different real-time operating systems out there. So it abstracts all the hardware away from you, so you can just go with their simple interfaces and not worry about it too much. It's really nice. It does make team development a lot better. Like, I can say, okay, I'm going to do this task, you do that task. And neither one of us has to write low-level drivers. which is great because that's where the feuds happen when you have a team of programmers trying to figure out, okay, well, I need to talk to the serial port. Well, I'm going to write, this abstraction from the serial port, and this guy over here says, well, I'm going to bit bang it instead, and yeah, it gets weird. So, question becomes, is it worth it to go to a real-time operating system? Maybe. Maybe not for starting out when you're just kind of learning. I don't know. But I will say, for the DC801 badge next year, I'm probably going to go with Chibios. So we'll see how that goes. All right, debugging. So now you've got your program written. How the hell do you see if it's doing the right thing? Or worse yet, you flash it, upload it to your chip, and it does nothing. And you're like, well, it was supposed to kick NEMIS every 5 minutes. Why isn't it doing anything, right? So here's some options for figuring out debugging. Really simple one is blink an LED. Use your GPIOs. Put a little instruction in there that says, I hit this part of the code, I'm going to turn an LED on. Or this conditional is true, I'm going to turn an LED off. Imagine this is from Whopper from whatever the name of that movie was. War Games, there we go. You saw all the LEDs on that. That's what those guys are, is debug LEDs to tell you what state the processor's in, right? So you could have your very own Whopper at your own home, The other nice thing you can do is if you're trying to figure out a real-time offset of signals, you can define a block of GPIOs and use a logic analyzer, and you can see that, oh, this fired 4 milliseconds after this fired. And sometimes that's super useful. So this is a very useful one, very easy, really low cost. The next step the chain is to set up a serial port. It may eat up some space because now you might have to pull in like the printf routines to be able to format strings and such. But your debug SPU can actually give you human readable stuff out the other end. So, and it's almost real time. I mean, the problem with getting it over a serial port is it has to clock all that data out of a serial port. So if you've got something that's really real time, this is a lot better. Whereas this guy, you have to wait for it to clock out. But a lot of times this is fast enough to do it. If your chip supports it, you can use JTAG. JTAG allows you to plug into the processor and reach deep down into that guy. You can pause execution, you can set up breakpoints, you can reach right in and alter memory on the fly. The only downside here is that if you're getting external data streams in, that data is streaming in and you pause execution, all that data is just going to shoot right over your head. So if you're trying to do real-time debugging, it's really hard to get the real-time debugging out of this guy. So let's talk about some tips and tricks for programming. Dynamic memory, bad. Remember the Ghostbusters, the stack pointer? Trust me on this, guys. I mean, it's really tempting to use malloc to grab yourself a chunk of memory, and like on an entire operating system, the operating system is going to prevent you from being a dumbass, right? It's going to cause your program to abort. But in firmware, hey, it's just going to lock up on your, or it's going to do something weird, or who knows, right? Maybe instead of kicking NEMIS every 5 minutes, kicks pip like every 10 milliseconds. I mean, So it also allows you to do static analysis of your memory, right? So if you write your code and you go to compile it and the compiled code is 5K bigger than your available flash space, well, maybe you don't need all those JPEGs you embedded in there or something, right? Be really careful about loops and recursion. So you're going to have that big main loop. You want to get stuck in that big main loop. That's good for you. But if you're going off to some other loop to do something, make sure that you've got some sort of return condition happening over there. If you forget and you bypass that return condition and now it never kicks NEMIS and you're wondering what the hell's going on, it's easy to get stuck in a loop if you're not careful about your return conditions. Limit your pointer redirection. So you can have a pointer pointing to a pointer, pointing to a pointer, pointing to La La Land, right? So be careful about that. Try to limit how deeply nested you have your pointer so that you're not like pointing to data space when you meant to point to program space. Further trips. Code defensively. Here's the only code I've got in the whole presentation. So don't be clever and compact. I know it's really tempting to use like every little bit of, oh, I don't need those curly braces up there. That's, who needs those curly braces? But the problem becomes, you do this today, and tomorrow you have do other task. You stick do other task down here, because you've got it indented, right? Well, a program comes in here and says, if condition do task, and then it always does do other task. And you're like, why is it always doing that other task? So I highly recommend be verbose and be obvious about what it is you're doing. Because drunk you from 4 nights ago that wrote that clever code is never ever going to live down sober you 4 days later when it's on the wire and you're trying to figure it out. Remember this one. Computers make very fast, very accurate mistakes. Okay? So try to think what the computer's doing, not what you want it to do. Like, you really want it to give you that sandwich, but it doesn't know how to give you a sandwich. It knows how to open the refrigerator and grab the mayonnaise, but it doesn't know how to turn that into a sandwich. So you have to think about the steps. Think about what the computer's doing. This is a very big truism. I see this all the time. I'll write something and I'll look at the code and I'm like, there's a race condition there. 1 in a million chance. It'll never happen. Yeah, it happens every 5 minutes. So when your CPU is executing in the megahertz, once in a million, it just happened. So be very careful about having little things that that can happen that you're like, oh, that'll never happen, because I guarantee it probably will. Lastly, I would recommend checking out NASA's rules for developing safety critical code. A lot of this stuff is pulled out of there as well, but they have like a list of like 10 rules to go by. And this is the rules that they've developed for developing safety critical code for, you know, Mars landers and such. It doesn't include unit errors though, so, you know, take that with a grain of salt. So, snide comments? Questions?
I liked it.
It was very informative.
Are you going to do like Firmware 201?
Yes, I definitely would like to. I'd like to do one where we come in with some processors and you guys write some code along with me and see how that goes. This was just kind of hopefully to get you guys thinking about the things that you need to worry about in firmware, and hopefully it demystified some of how this program actually execute on your firmware processor. So hopefully.